Hello everybody, I am Mika Seppälä. This podcast introduces you to some basic concepts of numbers, sequences, series, and to limits of sequences. First we start with numbers. The set of natural numbers are numbers 0, 1, 2, 3, and so forth. So 0 and all positive integers. That set is denoted by capital case boldface N, and often one uses notation which is called blackboard bold N, which is capital case N with two straight lines in the middle. So these are natural numbers. In some other texts, natural numbers start from 1, but we will consider also 0 as a natural number. Then we have the set of integers, capital case Z. That is 0 and then plus or minus 1, plus or minus 2, plus or minus 3. These are all positive and negative integers and 0. Ratios of integers form rational numbers. A rational number is of the form p divided by q, where p and q are integers. We can take q to be positive, and we may assume that p and q do not have common factors other than plus or minus 1. If we do that, then the representation of a rational number as a ratio p divided by q is unique. If we drop the assumption that these numbers p and q are not allowed to have common factors, then this representation is not anymore unique. Clearly, 2 divided by 4 is same as 1 divided by 2. So numbers p divided by q, p and q integers, q positive, and p and q do not have common factors other than plus or minus 1. These are rational numbers. And then we have also irrational numbers, numbers that cannot be represented as the ratio of two integers, and these irrational numbers together with rational numbers form the set of real numbers. The set of real numbers is denoted by capital case boldface R. The Greek letter capital case sigma indicates summation. For example, if we write summation k from 1 to 5, 2 times k plus 1, we mean the sum of odd numbers from 3 to 11. That is, summation k from 1 to 5, 2 times k plus 1 is 3 plus 5 plus 7 plus 9 plus 11. The right-hand side has been obtained by substituting all possible values from 1 to 5 in place of k in the expression 2 times k plus 1, and then by adding all these numbers. So in this case, the left-hand side is slightly shorter than the right-hand side, but in many actual situations, sums may be very long, and it may be either inconvenient or completely impossible to write them out completely as a sum, like the one on the right hand side. So the summation symbol is convenient and necessary in certain situations. For example, consider the problem summation k from negative 5 to 5 k cubed. This sum k from negative 5 to 5 k cubed can be evaluated by plugging in all the values from negative 5 to 5 in place of k, raising that to the third power and adding all these numbers. So we get that summation from negative 5 to 5 k cubed is negative 5 cubed plus negative 4 cubed plus negative 3 cubed plus negative 2 cubed plus negative 1 cubed plus 0 plus 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed. And then we observe that negative 5 cubed is same as negative of 5 cubed. So negative 5 cubed cancels out with 5 cubed, and in the same way negative 4 cubed cancels out with 4 cubed, negative 3 cubed cancels out with 3 cubed, and negative 2 cubed with 2 cubed, and negative 1 cubed with 1 cubed, and we are left with 0. So we conclude that summation k from negative 5 to 5, k cubed, is 0. This indeed is the case, and this could have been observed simply by remarking that k goes from negative 5 to 5, so this is symmetric with respect to the origin. For all positive values of k in the interval from negative 5 to 5, there is also the corresponding negative value, and these two values for k cubed cancel out, therefore the sum is 0. A sequence of numbers is defined by a function from the set of natural numbers to real numbers. So a sequence is simply a sequence of numbers, one following the other, a0, a1, a2, and so forth. These numbers a0, a1, a2, and so forth may be just any numbers. Sometimes the sequence starts from the value n equals 1. That is usually for notational convenience. For example, if we write 1, 1/2, 1/3, 1/4, and so on, this is a sequence whose general term is of the form 1 divided by n, but now n starts from 1 and then goes to 2, 3, and so forth. So this sequence S in this case is the sequence of numbers 1 over n, where n is a positive natural number. Sequences have limits. A sequence an has the limit b if the numbers an get real close to the number b as n grows. This is a heuristic definition of limits. Later we will give a precise definition what it means that numbers get arbitrarily close to some other number as n grows. Notation for the sequence an having the limit b is that lim as n goes to the infinity an equals b. In the case of the previous example of sequences, sequence of numbers 1 over n, it is clear that the limit of 1 over n as n goes to the infinity is 0, because as n grows, 1 over n gets arbitrarily close to 0. Therefore, the limit of 1 over n as n goes to the infinity is 0. Series is an important central concept in calculus. An infinite sum, capital S, which is summation n from 1 to infinity, an, where these an's are numbers, is called a series. And we wish to assign values for series. We do that by a limit process. We consider the partial sums. They are denoted by capital S sub k, and that is summation n from 1 to k, an. And these partial sums, they are numbers to be computed, even though the actual series has infinitely many terms and its value cannot be directly computed. The value of all these partial sums can be computed because they are all finite sums. So we get a sequence. We get a sequence of numbers sk, and we say that the series capital S converges if the sequence of numbers sk has a finite limit. And this finite limit is then the sum of the series capital S. Geometric series are particularly important. We say that a series capital S summation n from 1 to infinity an is geometric if the ratio of two subsequent terms is always constant. So that is, the expression a n plus 1 divided by a n does not depend on n, and we call this constant q. A geometric series can then always be written in the form the first term a plus a times q plus a times q squared plus a times q cubed plus and so forth. This is summation n from 0 to infinity a times q to the power n. This is a general geometric series. Q to the power 0 is by convention 1. Any number which is not 0 raised to the power 0 is 1. Now, an important question is to figure out when the geometric series summation n from 1 to infinity a times q to the power n actually evaluates to a finite number. We will later see that this happens always when the absolute value of q is less than 1. To summarize the discussion, let me recall that we have introduced the set of natural numbers. They are numbers 0, 1, 2, 3, and so forth. So 0 is a natural number, and the set of natural numbers is denoted by boldface capital N, and sometimes with so-called blackboard bold N, which is capital case N, with two parallel lines in the middle instead of one as in the normal font. So these are natural numbers. In some other situations by some other authors, natural numbers start from 1, but for the purposes of this course, natural numbers start from 0. Positive and negative integers together with 0 is denoted by capital case Z, and also here we have the blackboard bold font, where in the middle of the Z we have two parallel lines instead of one. Rational numbers are numbers of the form p divided by q, where p and q are integers. In order to get uniqueness to this representation of a rational number, we require that q is positive and that p and q do not have common factors other than plus or minus 1. The set of rational numbers is denoted by capital case Q. Rational numbers together with so-called irrational numbers form the set of real numbers. That is denoted by capital case R. A sequence of numbers is defined by a function from the set of natural numbers to real numbers, so they are numbers a0, a1, a2, and so forth. This is a sequence. And sequences have limits. The limit of a sequence an is b if the numbers an get arbitrarily close to b as n grows. Finally, we discuss series, and the most important of them is a so-called geometric series, which is of the form a number a plus a times q plus a times q squared plus a times q cubed plus and so forth. An abbreviation for this geometric series is summation n from 0 to the infinity a times q to the power n. Geometric series have a central role in calculus.